All right, so what you're going to do is follow me along in these notes, and what we're going to talk about is how we can use the basic concept of conservation of heat in a little bit more complicated way, looking at conduction. So here we have a basic system of conservation of heat. This would be our control volume. We can have heat in, heat out, heat generated, and heat stored. So it can come in or out by conduction, convection, or radiation. It can be stored through temperature changes, and it can be generated by energy conversion. So like resistive heating or friction or any other energy conversion process where we're converting something to heat. What we're going to do is use this to zoom in on conduction. So conduction uses thermal conductivity, which is described over here as a measure of how well a material transfers heat by conduction. This is kind of a basic range of thermal conductivities for different materials. And our goal is to use this to analyze conduction in complex objects. So what do we mean by complex? This would be an unknown geometry, possibly internal energy generation, and could be changes in temp. So this could be heating up or cooling down. So possibly a lot of things going on. That's why we're saying it's a complex object. So what we're looking at is what we're going to do is an energy balance on a small differential chunk of our object. So this isn't the whole object, this is just one little cube, and we have heat flowing through this in 3 dimensions. So it's of size dz, dy, and dx. We have energy generated and potentially energy stored, and again, we have heat flowing into, out of potentially all 6 sides of this cube. What we're going to do is zoom in just on the x direction, like this. So we're going to look at the energy generated inside of the cube, the energy stored in temperature changes inside of this cube, and we have heat flowing into the left side and, in this case, out of the right side. And that's a little bit arbitrary if we say which side is flowing in and which side is flowing out, but that will be fine. So this is our basic setup. We have heat flowing into the left side, out of the right side. And again, energy generated and maybe energy stored inside our cube. So our basic heat balance is in minus out plus generation equals accumulation. And this is fairly straightforward. So let's just plug things in. So this would be the heat coming in, that's Qx, minus the heat coming out. We're calling that Qx plus dx. What that means, that notation, x means we're coming in at this side, which is at position x. This distance from the left side to the right side is exactly dx. So that's why we get this kind of goofy notation of q at x plus dx. So that just means at the right side of our cube. Plus generation, so that's E dot G equals the accumulation or the stored thermal energy. So there's our heat balance. Now the challenge is we want to make this into an equation that we can use a little bit easier, so let's define our terms. So we have stored heat, generated heat, heat in at x, and heat out at x plus dx. The heat is stored as a temperature change. So that is the amount of thermal energy. It's internal energy. It's the mass times the heat capacity of the material times the change in temperature But we're going to be looking at the rate that this happens. So then that's divided by the change in time. That's the rate that energy is being stored. If we let delta t if we let that be small, that goes to a differential time dt, and then we get an equation where the stored energy is equal to the mass of our object times the heat capacity times d temperature d time. We can break this apart a little bit further because we can look at our object and we can say what the mass is of this object based on its size and its density. So mass is density times volume. If we go back up here, the volume of our object is dx times dy times dz, and the density is the density. We'll use the variable rho. So this gives us a stored energy of density times volume, dx, dy, dz, kind of a strange way to do things, times the heat capacity times d temperature, d time. Again, this feels kind of a strange way of doing things, but things will simplify as we start to put things together. Now, our generated heat is going to be equal to the amount of heat we generate per unit volume. So this is heat per unit volume times the volume. So again, that's dx, dy, dz, the size of our cube. All right. The heat in at x and the heat out at the other side, x plus dx, we'll treat those individually. So first we'll do the heat in at x. If it's by conduction, the total amount is the area of that side of the cube times thermal conductivity times d temperature dx. We need to put a negative in front of that because temperature flows downhill. So this is just kind of the basic Fourier's law of conduction, saying it's the area times the thermal conductivity times the slope of the temperature. Again, an equation that we've used before. We can make this kind of like the other ones by saying, hey, the area, if we go back up, the area where this is happening is on this side of the cube here. So this is dz, and this vertical length is dy. So the area of that side is of size dy dz. So this gives us qx equals minus dy dz, d temperature divided by dx, and I forgot the thermal conductivity K. So we're mostly there, but we have to now do the other side. So Q at x plus dx, another way we can think about that, this is equal to Qx plus how much Qx changes over the distance dx. Okay, so it maybe bears a little bit more explaining. So if I look at the value here, let's say it's 10, doesn't really matter what it is. If it decreases at some rate here, the value on the left side is going to be 10 minus how much it decreased. Maybe another way we could think about that, if we're decreasing at, say, 1 per unit length, and dx is 2 units of length, we would decrease from 10 down to 9 in the middle, down to 8 once we get to the right-hand side. And then our value at the right-hand side would be 8. The way that we're going to write that is going to be somewhat strange notation. it's going to be qx plus dx is equal to qx plus how fast qx is changing. So that's the derivative of qx with respect to x. That's how fast we're changing, times the length or the distance over which we changed, which is dx. Kind of a weird way to write it. Hopefully that makes at least some sense. Now what we're going to do is ignore that at the right for a second, and what we're going to do is put all of this together. So if we look back at what we were trying to do, we were trying to do this equation here. Qx, right, in minus out plus generation equals accumulation. So let's take all of these individual terms, the accumulation, the generation, the in, and the out, and let's put them all together and see what happens. So we have the stored energy, which is density times volume, dx, dy, dz, times the heat capacity, times d temperature, d time. So that's stored energy, E stored. So accumulation equals in, so that's qx, minus out, which is qx plus dqx dx times dx. So again, kind of a funky way to write things. Plus generation, which is equal to, so this is equal to qx minus qx plus dx plus generation, which is the volume times the rate of heat generation per unit volume. All right, so why did we do this kind of funky notation? Well, because we can see, maybe I'll do it in red, that qx and qx cancel out. So this gives us a way to simplify our equation quite a bit. We now have right, some extra stuff. We can say rho dx dy dz cp d temperature d time equals the x derivative of qx, which we wrote that up before, that's minus dy dz, times k times d temperature dx times dx. So we got dx's and dy's and dz's all over. All right, and then the last we can add is our energy generation term, which is the energy generated per volume times the volume of our object, dx, dy, dz. So dx, dy, dz all over the place. The last thing we need to do is take this negative sign here and put it down here. So I'm going to do that here in back in my blue color. So I have a negative there. So now a bunch of things cancel out. So I'll switch back to red so I can mark things up. This negative here and this negative here are going to turn into a positive. So those both are going to cancel out. That's going to be great. We also have a dx, dy, dz, dx, dy, dz on both of those terms. We have a dx on this middle term. And we have a dy, dz that's inside. So it's inside of this partial derivative. But dy, dz aren't are just the size of our cube. So those are effectively constants, so they can come out of that derivative. If something's not a constant, it can't come out of the derivative. We'll talk about that in a minute, but those can. So we have dx, dy, dz on all of the terms. We have two negatives. Those turn into a positive. So let's see how that's going to simplify our lives. That's going to give us density times heat capacity times how temperature changes with time. And that is equal to the partial derivative with respect to x of K, the thermal conductivity, times d temperature dx, plus Q dot. We still have a bunch of constants, so what we're going to do often in heat transfer is try to simplify things and get rid of some of the constants, and that's going to be actually kind of an interesting and good strategy in a lot of cases. So we have density, heat capacity, and K, and what we're going to do is define a new term. Now we can look over here at the right. This is called thermal diffusivity. We'll use the variable alpha, and that is going to be defined as K, the thermal conductivity, divided by density times heat capacity. So what thermal diffusivity is how quickly a material responds to changes in the thermal environment, how quickly it would heat up or cool down. So that depends on how quickly heat moves through the object, which is K, but also density times heat capacity, kind of how much heat gets stored inside that object. Density times heat capacity. So what we can do then is rearrange our constants, and we end up with d temperature, d time, equals alpha, our new variable, times d squared temperature d x squared plus q dot. One note on this, so to do that simplification from this that I showed in that step, we actually are taking K outside of that derivative. That is a reasonable thing to do mathematically sometimes. And it is when K is not dependent on X. So what that means is that the thermal conductivity, K, doesn't vary in the material spatially. Some materials actually do. Some materials, so if they're kind of unique and interesting, and like the thermal conductivity in one direction is different than the thermal conductivity in another direction, sometimes we can have kind of interesting, unique things going on. But for a lot of materials, K is just a number, like maybe 5 or 10 or 0.1 or 0.01. And in that case, we can do this math. And we're not going to really look at doing some of the analytical solutions. If K is more interesting, we'll look at analytical solutions like this one here. So this is a 1D heat diffusion equation. We learned a little bit how to derive this. We have to learn how to use it. And we aren't going to do it, but we could imagine doing this same analysis that we just did. We did it in the X direction. We could repeat it in Y and Z and get something that looks like this. So this is equation 2.21 in our book, where we have now an X piece, a Y piece, and a Z piece. We could also look at a little bit more exciting geometries, and we could get a radial piece, a piece in phi, and a piece in Z, the dimension down a cylinder. So the radial direction, the around the cylinder direction, and the down the length of the cylinder direction. Or as you see, it can get even more fun. We could have spherical coordinates have a radial direction. We could have a around and an around direction in our spherical coordinates. They all basically work the same. So they all are essentially different forms of just a more general equation, which we can write like this, where the partial derivative d time, d temperature, d time, equals the thermal diffusivity times upside down triangle squared temperature plus Q dot over rho Cp. So this triangle is the gradient operator. And what a gradient operator is, it's the slope. In this case, it's the gradient squared. So it's the slope of the slope, how quickly the slope is changing. How quickly the slope of the temperature, in this case, is changing. All right, so that's the basics of the heat diffusion equation. I know, kind of crazy equations, but hopefully as we start to get to use it and learn a little bit more, we'll get a sense of what actually this means and what we can do with it.